Welcome to this concluding class on nuclear physics. We'll be talking about nuclear models. So this is actually quite interesting and inspiring as well, because the nuclear forces are not as well understood as the Coulomb forces, but still just like atomic theory, one has been able to formulate nuclear theories as well. And there are nuclear models, at least two of them we are going to talk about briefly. But before that, we talk about binding energy, and this is a very important topic in the study of nucleons or nuclear physics. So the question is that what binds these nucleons, which are nothing but neutrons and protons that we know of now, what binds these things together? And we know that it's a short range force, and within a few Fermi meter it's very, very large, and outside the nucleus it has no existence, or rather it is not important with regard to, or rather as compared to the Coulomb forces. So let's consider deuterium as an example, which is 1H2, which has a proton and a neutron in the nucleus. So the total mass of a deuterium is equal to 1 H1, which is a hydrogen, plus a neutron, which is equal to 2.016490 units. However, the experimentally measured value is found out to be slightly less, which is 2.014102 atomic unit, which is about 0.002388 units lower than the value that we have quoted above. So this value is and this value, the difference between them is this. Okay, so this is the experimental value for deuterium nucleus. And so in terms of energy, if we multiply it by this 931.49 MeV per U, then it comes out as 2.224 MeV, and this is a fairly large energy if you think. And so we could ask this question, that how much of energy is required to break apart the nucleus of a deuterium into a proton and a neutron, and the value is indeed this value that we have got, which is 2.224 MeV. Okay. So any energy if you supply, the nucleus will be intact and will not have any emission, or rather the nucleus doesn't break apart. And if you give this energy, then of course the neutron and proton can be separated from the nucleus. And so this is for a general element. So we have given an example for deuterium, and so for a general element which is given by X, whose atomic number is Z and the mass number is A, the binding energy has this form, which is Z is the number of protons which you multiply it by the mass of hydrogen in these atomic units, and then Mn, which is the number of mass of a neutron, and so n is the number of neutrons. And just to remind you that A is equal to Z plus n, where Z is the number of protons and capital N is the number of neutrons. So this is the neutron mass, and then there is these term that comes, which is the mass of these the atom, and when you multiply by these the 931.49 MeV per U, one gets some value. These values will be decided by all these things, all these knowing these masses and so on. Okay, so this is the binding energy for any general element. And in fact, one important quantity that one needs to find, or rather is interesting, is that this is the binding energy per nucleon. Okay, so in fact, just to one step above, the nuclear binding energies are very high, and it ranges from 224 MeV to 1640 MeV for these bismuth 83209. And so we plot here the binding energy per nucleon, and there is the total binding energy divided by the total number of nucleons. I am sorry that this part of the text is not visible. You will see that when you get the slides. So what is written here is that from this plot, this is the place. Let me use a color here. So this is the most stable nuclei, which is that corresponds to 56 is a mass number, corresponds to Fe, which has got some value which is about more than 8 MeV per nucleon. It's actually 8.8 MeV per nucleon. So this value is about 8.8, and that's what is written there. And you see a peak here that's also interesting, and that corresponds to the helium, which is 2He4. So this 2He4, and helium is stable, and we know that helium is stable. There are alpha decays that happens, and helium nuclei, they do not undergo any further disintegration. So this corresponds to the first peak, that corresponds to the helium nuclei, and then the one that you see here is actually the most stable one, which corresponds to a mass number 56, and it's actually the iron. So now let's talk about fission and fusion. Let me just go back and to this binding energy curve. And then you see that the binding energy is plotted as a function of this mass number A, and after this 56, it sort of more or less remains constant. It just goes down a little as the mass number is more, but it sort of remains by and large a constant. I mean the value that you see here is just about 8 MeV, which is binding energy per nucleon. So that's the trend of this binding energy versus the mass number. Okay. Coming back to the fission and fusion. So when a heavy nucleus splits into two lighter nuclei, that's called as the process is called as a fission. Okay. So each of the daughter nucleons, they have binding energy to larger than that of the parent nucleus. I mean, it's not really used in this context, but I'm just telling you about this parent and daughter, because this one nucleus, maybe moderate or heavy nucleus, that splits into two lighter nuclei. So the lighter ones are called as daughter, and the heavy ones, which was initially there, is called as the parent one. So what can happen is that the energy given up in the process can be very large. Okay, and for example, if you look at uranium nucleus, it splits into two smaller nuclei without worrying about what they split into. There is binding energy that appears, which is like 0.0 MeV per nucleon. So you have 235 nucleons. So if you multiply 235 by 0.8 MeV per nucleon, one gets an energy which is equal to 188 MeV, and this is actually a huge energy emerging out from a single event. Okay. So even heavier nuclei would yield more energy. So this is fission. One actually gets very large amount of energy. On the other hand, when two light nuclei, they combine to form a heavier nucleus, the resulting process is called as a fusion. Okay. So these words are somewhat familiar even in the context of English language, that they fuse in order to become one. So two lighter nuclei would combine to form a heavier nucleus, and the fusion is a notable source of energy production. So a single nucleon of moderate size also means that more binding energy in the resultant nucleus, that is the one that's forming out of this fusion. For example, if you have two deuterium nuclei that combine to form a helium nucleus, about 23 MeV energy is released. So in fact, this nuclear fusion is the main source of energy for the sun and the stars. And the fact that nuclear binding energy is non-zero, it means that the nuclei are more stable, and they account for diverse forms of matter to exist. So this binding energy is an important and indispensable component of this discussion of the nuclear structure. Okay, so let's look at the binding energy curve in a little more details, and this gave rise to a liquid drop model. Okay. So, this short range nuclear forces, they are completely different than the electromagnetic origin, which is what we have told earlier, and hence they are very different in nature from the Coulomb force. And they are not well understood as well, because Coulomb force from the classical perspective, it's very well understood. But of course, that did not stop the nuclear models to develop and tell us more about the nuclear structure and the nuclear levels. And to understand how strong the force is that exists inside the nucleus, which we have rather termed as strong force. So, up to a separation of 3 Fermi meter, and Fermi meter is so 1 Fermi meter is like 10 to the power minus 15 meter. So, within this distance, the attractive force, say the attractive force between 2 protons is 100 times larger than the repulsive force between them otherwise. Otherwise means that if we are not talking about them to be inside the nucleus, but they to be like 2 charged particles interacting by an electromagnetic force or Coulomb force, then this within this nuclear range or nuclear radius, they are about 100 times larger. Okay, this is the force between 2 protons. Okay. And similar forces exist between similar large forces rather exist between neutrons or neutron and proton. So, either we talk about the force or we talk about interaction energy, both mean the same thing. Now, thinking of nucleus with a drop of liquid was quite innovative, and it was conceptualized by Gamow in 1929 and Weizsäcker in 1935. That accounts for the binding energy per nucleon versus A, which is basically the curve that you have seen here. Okay. And similarity with that of a drop of liquid and not solid can be understood, because even the solids actually they interact, the ions interact by nearest neighbor spring like force, but the vibration that it causes because of this this spring like motion, or rather they are connected by springs, is enormously large and will harm the the stability of the nucleus. So, the solids were kept out of the discussion, and the only analogy that was found was with that of a liquid drop. And the nucleus is thought to be like all those nucleons, they are free to move as the molecules of a liquid, but they maintain the fixed intermolecular distance between them, and such that these all the nucleons also stay within the nucleus. And this is an important part of discussion for these liquid drop model. So, if you consider the energy associated with each nucleon-nucleon bond is given by some u, so this u is actually negative, because that's like a binding energy, it's a bound state energy, so it has to be negative. But then this is, when this is quoted as a binding energy, which is what we have seen, and we have quoted this binding energy to be positive. So, the when it's converted, or rather talked about in terms of the binding energy, then of course we do not talk about this energy to be negative, rather we quote positive values for the binding energy. So, say if this is like there are there's a nucleon here and there is a nucleon here, and then there is some bond between them, and if the binding energy is u, and which is shared by each one of them like this, so then the binding energy is u by 2, it is shared by 2 nucleons. Now, assume the nucleus to be spherical and the nucleons to be spherical in shape as well. So, you see this dotted line, that is the nucleus, and then there are these open circles and these darkened circles, or these colored circles, and these are the nucleons that are there inside. And if you think that these are like liquid drops which are interacting with each other, or rather these liquid molecules are interacting with each other, but maintaining a shape, because the nucleus has to maintain its shape, it cannot, it can go a slight bit of distortion, which eventually gives rise to the quadrupole moment, but it cannot completely change its shape. So, the shape would remain constant, and that is why it is like these intermolecular forces in liquid. And when you think about that each sort of nucleon which is inside this sphere, it is in contact with 12 other spheres, and these 12 other spheres, each one will have a binding energy of u by 2. So, this nucleus has a binding energy of u, 6u, okay, 6 times u. And for a number of nucleons, it is 6 AU, where A is the mass number. So, that is the binding energy. And this binding energy, because we are all talking about these nucleons to be enclosed within the nucleus. So, we are talking about this volume binding energy. So, we call it E volume, which is some constant times A. Of course, this constant here is equal to 6U. That's constant is immaterial. So, it is written as A1 into A, small a1 into capital A, where capital A is the mass number of the element. So, now there are also nucleons which are at the surface, and these nucleons do not have neighbors on the other side, just like an inside one, say here has a neighbor on all sides, the one here does not have a neighbor on all sides. So, they have less than 12 neighbors, as we have talked about for these ones that are inside. So, an estimation of the surface energy can be done. So, the total binding energy gets reduced by the surface energy because of these the energy is less for these nucleons. And how do we make an estimate of this surface energy? We can take the surface to be 4 pi r square, where capital R is the radius of the nucleus, which we can write it as some r naught square, where r naught is a constant. So, it is r naught square into a to the power 2/3. As opposed to A in the volume term, this involves a term, the surface term involves a to the power 2 by 3. So, this surface terms, so this peripheral nucleons, or which are on the surface, they reduce the binding energy by this amount, which is A2 into a to the power 2 by 3. So, the binding energy becomes actually EB equal to E volume and plus E surface, and at this stage it becomes equal to A1 A and minus A2 a to the power 2 by 3. So, E surface is actually considerably large for lighter nuclei, because most of them it's like very few of them are inside and most of them actually are lying on the surface. Okay. So, there is a competition between two, yielding the surface or properties of a liquid. Now, how is this related to the property of the liquid? So, if you drop a liquid onto a non-weighting surface, it does not weight the surface, and then you will see that because of the surface tension, it tries to minimize its energy by making a sort of spherical in shape. You can see that when you boil water. So, the saucepan that you boil the water on, if you look at when it started boiling, you will see that there are bubbles formed, but the bubbles are still stuck to the bottom surface of this pan, and then when the thermal energy increases, these bubbles become bigger and then they get detached. So, the surface tension is no longer able to hold them together. So, they kind of detach from the surface or from the bottom surface. Okay. So, this is just like a liquid drop on a non-weighting surface assumes a spherical shape. Because of surface tension, the energy of this configuration is minimized. Configuration means liquid drop or the spherical shape is is forms because to minimize the energy, and we see a similar thing as well here, that these surface term is actually bringing down the binding energy, so that stable nuclei are formed. So, this justifies the name liquid drop model, and we have these this electric repulsion or rather these Coulomb term also they contribute to this binding energy or lowering of the binding energy. And how do they do that? Consider that the Coulomb energy to be the work done in bringing Z protons from infinity to the nucleus, or this spherical region in the nucleus. So, the potential energy for two protons to be at a distance r apart, r is any distance, so V of r becomes equal to minus E square by 4 pi epsilon 0 r. Now, if there are Z protons, there are Z into Z minus 1 by 2 pair of protons. What I mean is that these protons are all indistinguishable. So, out of this Z, if you have to make two protons as pair, the possibility, or rather the number that you can come up with for the number of pairs is Z into Z minus 1 by 2. So, these are the pair of protons, and there is a pairwise interaction. So, we have this Coulomb term to be equal to Z into Z minus 1 by 2 into V, where V is this minus E square by 4 pi epsilon 0 r. And if you write this r to be equal to 1 by r average, there could be these because you are considering all pairs of protons. Some of the protons can have different distance than others, but for a uniform packing, this is 1 over r average would be a good approximation for these distance r. So, you replace 1 over r by 1 over r average. So, that is the average distance over all these proton pairs. So, assuming the protons to be uniformly distributed, that is 1 over r average is like 1 over r, which is r is the radius of the nucleus, that goes as a to the power 1/3. Okay. So, that is like because your 4/3 pi r cube is like your a. That is the volume term which we have seen that it is equal to A. So, the Coulomb term comes out to be something like Z into Z minus 1 divided by A to the power 1/3. So, we have one term that goes as A, then another term goes as minus A to the power 2/3, and this also will be a minus, and this is A to the power 1/3. So, the binding energy becomes equal to A1 A, A2 A to the power 2/3 and A3 Z into Z minus 1 divided by A to the power 1/3. And when you plot this, you see different energy scales. So, this again this binding energy per nucleon is plotted, which is what we have shown earlier, and you see that the surface energy grows like this. So, this is the surface energy curve, and then the Coulomb energy falls like this, and the volume energy is like this, which is linear in A. So, that is like a constant. So, a combination of that gives you this total energy, which gets reduced by these the Coulomb term and the surface term, and you get a form which is very similar to what you have seen in experiment. So, this is the triumph of this liquid drop model, and all these are in analogy with a liquid drop, and that is why this model is quite successful in explaining the properties of a nucleus, or these energetics, rather the binding energy of the nucleons. It explains it well. But there is another model called as the shell model, and there are emergence of certain magic numbers which are like the nuclear shells, all these nucleons. These are these magic numbers which are the number of nucleons occupying various energy levels and so on. So, we have seen that the assumption of the liquid drop model was that each nucleon interacts with its nearest neighbors as in a liquid. Okay. But there could be a more general kind of interaction between these nucleons, which is not taken into account in the liquid drop model that we have seen. Okay. Now, let us try to bring back the atomic picture, and these atomic pictures, there are these if you look at the periodic table, these inert atoms or inert elements such as krypton, xenon, neon, etc. They have these atoms have these 2, 10, 18, 36, 54, 86 electrons, whose all the shells are completely filled. Okay. And these inert elements, and when we say inert, we mean that they do not actually interact with anybody, okay, or anything, any other element and make a compound. So, they do not take part in any kind of chemical reaction, and that is why they are called inert. And do we have a similar scenario in nucleus, that do we have such nucleons, specific number of nucleons which are inert, chemically inert? Now we cannot say chemically inert, but we can always say that they are stable. And if they are stable, they are abundantly available. So they are available in abundance, and this is what it says. So these are the numbers for for the nucleons like 2, 8, 20, 28, 50, 82. These nucleons are found to be exceptionally stable, just like these ones which are stable. Stable means they are chemically inert. Okay, and here stable means that they are found in abundance. For the nucleons or the nucleus is inert, means they are found in abundance and they don't undergo any decay and cannot be broken up, and these are subsequently called as the magic numbers. Okay. So these shell model actually explains the existence of this magic numbers. We won't go too much into details because these nuclear interactions are not very well understood. So precise form of U of R is unavailable. And if you think the form of the nucleus is either something like this, or ones with slightly curved sort of edges, or they are like the ones that is like this, and so on and so forth. And they what I mean to say is that they are like repulsive, and then they are like attractive at large distances, and so on. And if you solve Schrodinger equation, or if you take something like a harmonic oscillator, they haven't yielded very well description of these magic numbers at least. And so if you solve Schrodinger equation, if you can solve, at least for this case it can be solved, but otherwise this you'd find it very difficult. But they don't give rise to any magic numbers. And what comes to rescue is that the spin orbit coupling, or the LS coupling for the lighter nuclei, and JJ coupling for larger nuclei. In fact, JJ coupling occurs in most of the nuclei. We have talked about this earlier. The LS coupling, if there is a spin and orbital coupling, and that happens when you take these electron in the rest frame of the electron, the proton is moving around it, and a moving charge, because the nucleus is charged with the charge of a proton. So a moving charge is like a current, and so the electron actually experiences a magnetic field due to this current, and the spin of the electron couples with the magnetic field via Zeeman coupling, and this will give rise to a L, and this can be shown to have a L dot S kind of thing. And one artifact of that is that you cannot use either L or S, but you can use a new quantum number or a new operator called J, which is equal to L plus S. So this LS coupling that occurs for lighter nuclei, and one has JJ coupling for larger nuclei. And just to tell you a little about this JJ coupling is that, so S and L of each nucleon, they couple to give a value of J, which is the total angular momentum, and J is equal to L plus S. Okay, so well, L is the orbital angular momentum, and these S is the spin angular momentum. So the various J's can couple to give the JJ coupling, and the spin orbit interaction that splits each of the state for a given value of J into this 2J plus 1 sublevels, and with allowed orientations of this J vector, and the numbers available, if you carefully do all these calculations, then the numbers available in each of the nuclear shell is 2, 6, 12, 22, 32 and 44. I did that quite briefly because I didn't want to get into the details of that, but what you should know are these, that there exist these two models, the liquid drop and the shell model, which can by and large explain all the nuclear properties that we are familiar with. So with these numbers that are available for this nuclear shell, we can have these many number of nucleons, either they are neutrons or protons, and these are the magic numbers that one is familiar with. Okay. So that's a triumph of this shell model, and the success is not only in explaining the magic numbers, it is also capable of explaining the nuclear magnetic moment. So for proton and neutrons to have even numbers, so if it's an even nuclei, both of them to be even, the angular momentum will be integer, or they may cancel out, giving you, so these are 0 or integer values. And for an even odd or an odd even combination, it yields half integral value of the angular momentum, and similarly the odd combinations yield integral angular momentum again. So the observed values of angular momentum for the nucleus are these values are well explained by this shell model. So the liquid drop model sort of explains the binding energy and various energetics of these like these various magic numbers that you get, and as well as the observed angular momentum values of the nucleus are explained by this shell model. So we shall stop here, and that concludes our discussion on nuclear physics. We have kept it very brief, and the ones that we have discussed is the nuclear structure, how historically it became clear that the nucleus really consists of protons and neutrons, and then we have talked about radioactivity, and here briefly we talked about this two models and the binding energy of the nucleus. So I'll stop here. Thank you.